scripting folder on the usual REU 2023 GitHub repository. And the idea is to show how you can use GNU Radio to conduct something which looks more like a real-world observation with a radio telescope. But instead of using a radio telescope, I'm going to use the RTL-SDR stick. So what we are going to be doing is to do some observations, to do some measurements of radio frequency signals using the RTL-SDR, and basically scripting GNU Radio from Python so that you can see how you can control any parameters of your receiver. In a real-world telescope, you might have to run some calibrations, adjust gain settings, point the antenna, and those kind of procedures to conduct a real-world observation. With one of these SDRs, there are not so many parameters we can modify. So what I'm going to do to demonstrate is to observe at different frequencies. So we will be changing the frequency of the RTL-SDR every time we observe. And the idea is to look at different portions of the RF spectrum. And even the example I'm showing today might be useful for radio frequency interference monitoring, or to get a picture of how the local radio frequency environment looks like. But what I want to make clear is that the Python code here can be made more complex if you have a real-world telescope and you need Python code to point the antennas. It will be easy to see where in this Python script you can insert calls to point the antennas, adjust gains, start whatever procedure that needs to be done. So hopefully this is some base that you can build from. Here I have a blank flow graph. I have the finished flow graph on the GitHub repository, and I'm going to be copying and pasting a few sections from it to save time, because those sections are something we have seen already in previous sessions. So what I want to do first is to set the sample rate. As we saw before, 2.4 megasamples per second is a good sample rate to use the RTL-SDR stick. I'm also going to do to set a name here, so test observation, for example, and it doesn't matter, we don't have a title. I'm going to save here, test observation, and the original flow graph is called something like RTL-SDR receiver flow graph test. And this is important because when we go to Python, we will need to use the name of the flow graph. So test observation, this is going to be called. And what I want to put here is the RTL-SDR source. Tune it to what frequency? 98 megahertz, I think I have, but I want to do that using a parameter. So when we want to control any variables of a GNU Radio flow graph externally, every time we run the flow graph, we can use the parameter. So I'm going to search for parameter, and here we have the parameter block. This parameter is going to be used to obtain something that looks like a command line parameter when you run the Python script that is generated using the flow graph. And it also looks like a function parameter if you call the Python code directly. Within Python, we will see how those methods of calling the flow graph work. So for this parameter, I'm going to call it frequency. This is the frequency we will observe at. The type is going to be float, and I'm going to set 98 megahertz. This is the FM broadcast band. So at the beginning, we are using some FM radio stations just to demonstrate this flow graph. Let me copy and paste the GUI frequency sync. Let me see if this works. Oh, it doesn't. Seems I need to copy and paste within. What am I pasting from? Yeah. Okay, anyhow. So this is pretty much what I had in the first session, actually. It's the RTL-SDR stick, and we are displaying the frequency. If I run this just to check that my SDR is working. I can see that maybe turning up the FFT average. Yeah, something doesn't look quite all right, because I would expect the station at 98.8 megahertz, and I don't have it. Maybe I have, okay, I see. So in here, channel 0 frequency 100 megahertz, it comes with a 100 megahertz default, but I forgot to insert frequency here. So just the name of the parameter. Parameters work in more or less the same way as variables, in the sense that you can insert their name in any place where you are supposed to be filling in a number or a Python expression, and this will take the value of the parameter. So we can see this is 98 megahertz, but then we will see ways in which we can modify the 98 megahertz value externally. Okay, so now this looks more like what I expected. This is 98.8 megahertz, which is a strong local radio station here. Okay, what we want to do is, as you saw before, the FM radio station is not occupying all the 2.4 megahertz bandwidth that the RTL SDR stick provides. So we want to record the signal. We want to record IQ samples. That means raw complex voltage samples. And if we were to record at the full data rate, that would be 2.4 million numbers per second. And we are going to record complex numbers in floating point format for simplicity. So that's 8 bytes per sample. So 8 bytes times 2.4 is already 9 point something megabytes per second. So that gives rather large files quickly. What I'm going to do is to decimate the signal of that FM radio station to show you how you can crop an area of the RF spectrum, which is of interest. So again, if this is our FM radio station, we can see that it only occupies about 200 kilohertz. So from 0.7, this is 0.7 to 0.9, this 200 kilohertz is where our FM station is placed. We want to crop this 200 kilohertz region. And to do so, we will use the frequency translating FIR filter block. This has appeared in previous sessions. And in fact, in the second part of today's tutorial, we will see more in detail how to set up this block, the frequency translating FIR filter. So once again, what this block does is it moves to baseband, so to 0 hertz, the signal of interest. So you can think that this is going to be moved to 0 megahertz here. And then it decimates and filters to the required decimation ratio that we specify. And we are going to specify a ratio so that we end up with only 200 kilohertz rather than 2.4 megahertz. Okay, so that's the idea. How can we do that? The way to do that is frequencies translating FIR filter, and then the decimation factor is equal to 2.4 megahertz divided by 2 kilohertz, and that's 12. I could also do 2.4 million divided by 200 kilohertz, and the only problem is I need to round this to an integer because green means integer. So this is 12. That's maybe a more clear way to do it. And then this is the part that we will see in more detail later. So for now, just bear with me. I want to type here the low-pass filter definition, which involves the gain. The gain is usually set at 1, the sample rate, and then the cutoff frequency, which is basically going to be 0.5 times the sample rate, and the transition bandwidth, which is, this is a typical choice for a filter. As we will see, it doesn't give a very long vector. It's only 25 taps. The longer the vector, the more calculations that the computer needs to do. So the more CPU intensive it will be.
So we've got a question here, Daniel.
Mm-hmm.
Could you read what you typed in that box? It's kind of hard to see with the colors.
In this box, you mean?
Yeah.
Okay, maybe what I can do is to copy and paste on the Zoom chat, because I can read, but it's kind of a mouthful. I will copy and paste in the Zoom chat in case it's helpful, and then also try to read. So this reads like filters, which means filter description, I guess, dot Lowpass for the Lowpass filter method or function. Then there's a parenthesis for function arguments, 1.0, which is the gain, comma, sample rate, comma, then 0.5 times the sample rate. That's the cutoff frequency. So we are using a cutoff frequency of half the sample rate. And sorry, I'm doing this wrong. I need to divide by the decimation. So this now properly reads 0.5 times the sample rate divided by the decimation, which is 12. So divided by 12. And then the final argument, so there's a comma, and the final argument is 0.1 times sample rate divided by 12. So I'm going to paste again the correct expression on the Zoom chat. And I don't know if I can make this larger, the flow graph I can, but this one I cannot. So hopefully you can see better now. Okay, does this help?
Yeah, it looks like it compiles now.
Okay, great. So let me see what else. The sender frequency needs to be the frequency that our signal of interest is, but within the bandwidth of the RTL-SDR. So the radio frequency signal is at 98.8 megahertz, but the RTL-SDR is centered at 98 megahertz. So our signal appears at 800 kilohertz. I'm going to type here 800 E3, which means 800 kilohertz, and then sample rate as it comes by default. Maybe what I can do here is to make this larger, and hopefully it is easier to see, although in here you don't get the complete expression. So to show what this frequency translating FIR filter does, and also to check that I have entered all the values correctly, I'm going to use another frequency sync. And now I need to know that I have divided the bandwidth by 12 to yield 200 kilohertz. So hopefully this will come out, yeah, 200 kilohertz. So now I can see here 200 kilohertz. And the rest of the parameters are the same. So if I run this, here in the top, I see just my FM station. So this plot should look like this. And here in the bottom, I see all the FM radio stations, or at least 3 FM radio stations. And with some lag, when the signal changes because of someone going quiet on voice or whatever, you might see that in the top plot, it's doing the same thing. So, okay, basically we have accomplished cropping these 200 kilohertz as if I were to do this selection. And of course, I have increased the resolution on the FFT. See, it's the same signal. I have increased the resolution on the FFT because this is 4096 points for the 200 kilohertz, and the one on the bottom is 4096 points for the 2.4 megahertz of spectrum. So, okay, so far, nothing new. The next thing I want to do is to record to a file. And let me see if I can, yeah, this is the one I want to copy from. So I'm bringing another parameter, which is the IQ file output. This has the type string because the file name is going to be the path of a file. So it's going to be a file. And since I'm using Linux for this, by default, I don't want to record anywhere. So I'm doing /dev/null. That's a special device in Linux that basically discards all the input you write to it. If you are using any other operating system, you might place here the name of a dummy file and you will be writing to a dummy file. You you will throw away later on. The reason I'm doing this is because we will be using a Python script to call this flow graph several times to record at different frequencies. And for each of the frequency, we will use a different file name for the output. And it will be the script, the one which is setting the file names. So that's my parameter. And to record to a file, we use the file sync. So file sync here in the file, IQ file output. That's the name of the parameter. And something to point out is for simplicity, I'm going to record in complex format. This saves me the need to convert because everything here is blue, so everything is complex format. And then I can record directly in complex format. If I were recording for a very long time or at a large sample rate, it's a better idea to use short, which is 16-bit integers, or byte, which is 8-bit integers, to save space, because as I mentioned, recordings can get pretty large pretty quickly. But if you use one of these, then you need to convert. And also the more inconvenient aspect to using short or byte is that floating point numbers essentially have no limit. They can become virtually as large or as small as needed. So you don't need to care about the amplitude of the signal. However, if you represent the signal, let's say with bytes, the minimum value you can have on a byte is minus 128, and the maximum value you can have on a byte is plus 127. So you need to scale your signal so that it lies between minus 128 and plus 127. If you do this wrong and your signal is larger than this 128 limit, then you will get clipping. Any number, any amplitude which is larger than the limit will get replaced by the maximum possible value. And if your signal is very small, for example, if the maximum value is 3, then essentially you're using very few output values because your signal might cover only the range from -3 to +3, so you are not fully utilizing this 8-bit range, and as a consequence, you are going to get some nasty quantization noise. So you need to be careful when you are recording in byte or short format, but not in complex. In complex, pretty much we can represent any amplitude value accurately. So that's the reason I'm recording in complex. And then what else do I have? Yeah, probably I can do a quick demonstration of how this records. So to do a quick demonstration, I set just a dummy file name, and I'm going to record in /temp/recording. If you're using Linux, this is the temporary folder, which might be even in RAM so that you don't use the hard drive. Or even if you use the hard drive, it's cleared every time you reboot the computer. So it's a convenient place to put temporary files. If you're using Mac OS, I think there is something similar. If you're using Windows, probably there's also a temporary folder, but it would be probably easier to type in here just any file name, and it will be saved to the current directory or to the directory where you run the flow graph from, which, by the way, you can see here in the console. So, okay, I didn't save this temp recording. Let's save, and let's run this just for a few seconds. It's okay. I just want to check that the recording is working. So I have here a terminal, and we do have a file which is called temp recording is 9.2 megabytes. So the sample rate is quite low, 200 kilohertz. We only recorded for a couple seconds, so that's reasonable to expect. The software I'm going to use to display this recording is called InSpectrum. And in Linux, this works really well. I'm not sure how easy it is to build on Windows. Probably it's somewhat difficult. And in Mac OS, no clue. So InSpectrum, if you're using Linux, it's quite recommendable. There is something else that you could use because it's multi-platform, which is called IQ Engine. And this runs on the web browser. And in fact, it has a bunch of recordings done by the GNU Radio community, also by myself, by Northeastern University. But the feature I want to demonstrate is that there is something to open local files. So if you have something which is formatted as a SIGMF file, that's the disadvantage of using this tool, that it needs a SIGMF file as input. Then you can open it here and examine the spectrum with the web browser. So that can be a convenient option, and maybe I will demonstrate this in a future tutorial. So, okay. I'm going to use in Spectrum, and the only parameter I need to supply to it is the sample rate as 200 E3, because it already uses the same floating point complex format by default. So temp recording. And then I probably want to play with the FFT setting just to make this nicer. And we can see this is the waveform of the FM radio station. The shape of the carrier changes as music is going up and down in volume. And we have about 6 seconds of data. So this is the kind of recording we have obtained with the flow graph. You can also play this back in GNU Radio. There's a waterfall sync, which will show something more or less similar. In fact, maybe it's good to show it now. But it's probably not as good as using in Spectrum. So let me set this back to dev null.
And Daniel, there is, I'm just looking at the InSpectrum GitHub, there are instructions there for building on Mac using Homebrew or Mac ports, so that is possibly an option.
Oh, yeah, that could be handy. I didn't realize that. Where did you see that?
If you go to the build instructions link there.
Okay.
And at the bottom, it says building on Mac OS X.
Yeah, so maybe this works. Actually, I could try to reach out to some folks using macOS to see if this works, but I guess something has used it successfully, otherwise it wouldn't be on the instructions. So if anyone of you decides to try, just let me know if it works. Thank you, Steve. So as you can see, it's more or less the same thing on the GNU Radio using the waterfall sync, and you could do a flow graph to play back your recording into a waterfall sync. So that's another way of browsing through the recordings. Of course, it's not so convenient because when you do this in GNU Radio, you are essentially playing back the recording. And when you have in Spectrum or IQ Engine, you have a slider and you can go back and forth in time as you want, as if the recording was an image and you were moving over the image. So, okay, I don't need this. Let's disable it. And the next thing we're going to do is to obtain waterfall data or spectrum data, because that's a very common way of recording in radio astronomy or in SETI. Instead of recording raw IQ data, which is very, very large, we record power spectrum of the signal versus time. That's much smaller than the raw IQ data, and it's also easier to process. So if you are trying to detect some signals because they appear at a certain frequency with a certain power, as we often do in narrowband SETI searches, then either way you are going to end up computing your signal power spectrum, so you can record directly in the power spectrum. And let me copy and paste this and show you what is exactly this, but it is basically the same thing we had in the previous session. So we have the FFT size, 2 to the power 16. This could be any number we wanted, depending on what frequency and time resolution we want to get. Integration time in seconds. Let's make it 1 second. Why not? That's a convenient value. if you don't want to get too much output, if you don't have signals which appear and disappear very quickly, if you have signals which are really fast, like short bursts, then integration times might be short, milliseconds or even hundreds of microseconds. But with signals which are relatively steady, 1 second is a good value. And then here I have the integrations, and this is complaining because name MP is not defined. I'm using NumPy to round this number. So this is an import block for importing NumPy that I can also copy and paste. So now this is happy, and I can go and show you. What I'm doing is I have my IQ input, but I want to make it the full spectrum. So we are going to record the waterfall data or the spectrum data of all the 2.4 megahertz. We could change this if we wanted, or we could have 2 outputs. So already you see how much flexibility this gives you. You can have as many of these filters you want to select different frequencies. If you are interested in different frequencies, you could run each of these to its own chain like this to compute spectrum and save to file. So anything you want, you can just arrange the flow graph to do it. So stream to vector NFFT, because remember the FFT block works with vectors. Then FFT size. And as the window, I'm using the Blackman FFT window. This is a pretty common FFT window. It gives a good mixed performance between the performance parameters that we saw on the previous session, such as leakage, scalloping loss, etc. The rest are default, so we go forward and we do the FFT shift. Complex to magnitude squared to take the power. Then we integrate for 37 integrations. So these integrations is as in here. We divide everything by the number of integrations to compute averages rather than sums. And then file sync, spectrum file output. So this is another parameter which I need to copy. So spectrum file output. And something you might also want to tweak depending on your application is OpenFile and also unbuffered. So OpenFile does what its name suggests. So you have 2 options. Overwrite means when you write again to the file, it removes all the previous output and starts from the beginning. And append means append. So if the file already existed, then this preserves all the existing data and writes at the end. So depending on what you want to do, either append or overwrite will be the suitable choice here. And unbuffered, typically you want to set this off. What unbuffered means is not to use buffering. So what does buffering mean? Buffering means that instead of doing small writes to disk anytime that some data arrives into the file sync block, the file sync block waits a little bit and then writes the data in larger chunks. That's called buffering in computer science. And that is good to do because of performance. It's better to do fewer writes of a large size than many writes of a smaller size. But if you are writing something very slowly because you are integrating for a very long time, or you're producing very few output samples, then you might want to set unbuffer to on, because if not, you would need to wait for the output buffer to fill up before you see some output on your file. This is, of course, if you want to look at the file while it's been written. If you plan on running the flow graph for a while, then closing it and finally looking at the file when the flow graph has finished, then there is really no difference in unbuffered and buffered for the sake of the contents of the file. For the sake of performance, unbuffer off, so that means buffering, is always preferable. So the file sync. And we also have something new, which is the VectorSync. And the VectorSync is here. Where is it? VectorSync. And the name might be confusing because it has the name vector on the name, but that doesn't mean that you need to use the VectorSync with vectors. Here we are using vectors because we are using the FFT block. So we have vectors, but it's perfectly fine to use the VectorSync with a regular stream of IQ samples, such as in here. So this is an example of the VectorSync not using vectors. So then the reasonable question is, if the VectorSync doesn't have anything to do with vectors, why is it called VectorSync and what does it do? So the documentation page has some information for us, and maybe doesn't get to the point of why it's called VectorSync. And the reason it's called VectorSync is because it's recording data not to a file, but to a C++ vector. A C++ vector is like a Python list or like a NumPy array. So it's a data structure which is able to hold in memory a list of numbers or other items. And this is what the VectorSync does. So rather than recording to a file in disk, it's recording to a data structure in memory that then we can access with Python or with C++. And this already gives a small example about how to do that, but we will be seeing this in more detail. Basically, we need to call our VectorSync using its name, and then use the .data to get the data. So that's the way to get the data in Python, and then we get this as a Python list, so we can do anything we want, such as print the data or run some computations and plots. There is a parameter in the VectorSync, which is reserve memory for how many items. If you want maybe the best performance, or you are pretty sure what's exactly the number of items you are going to record, you might want to set this. But otherwise, it's perfectly fine to reserve 1 item or 1024 items or even 0 items, because this is the initial memory reservation. So if more data than what you have reserved comes in, then this will allocate more memory, and it uses dynamic memory, so it can record until the memory on your computer fills up. So, okay, VectorSync. Because we want to refer to the VectorSync in a in a Python script, sorry, we would better set a descriptive name for the VectorSync, but by default, the names of the blocks are hidden because commonly you don't need to set the names of the blocks. So what I want to do is to set view show all block IDs. So this option, view show all block IDs. Then you can see that each block has its own ID. It's something which is auto-generated using the type of the block, such as, for example, these file sync blocks, file sync 0, because I only have 1. If well, no need to pull in a second one. So the second file sync, it's called blocks file sync 1. And this is called Spectrum VectorSync because I copied and pasted from Flowgraph, which already had this set. But by default, you would get something like blocks, VectorSync 0. And if you have many, it is easy to forget which one is the 0, which one is the 1. So my recommendation is use descriptive names. So for example, in this one, since it's going to record the spectrum data, spectrum VectorSync, and no need to have the 0. So that's the way to set the ID. And once we have set the ID, we can hide them again. Okay, let me see if I'm missing anything. No, I think I have everything. So by this point, my flow graph here looks basically identical to the flow graph which is on the repository. And now what I want to show you is one way to interact with these parameters. So I have generated the flow graph. Clicking this generate the flow graph button, I get a Python script And then if I go to the terminal, this is my test observation Python script, and I can run this with / test observation, or even Python 3 test observation, or something. It depends on your system. And I can do help for the help. So you can see that for each of the parameters I had on my flow graph, I get a command line parameter. So frequency to set the frequency, IQ file output to set the path of the IQ file. And I get default values, which correspond to the default values I have set in the flow graph, but I can override any of these. So for example, let's try to do a test observation, but the spectrum file output, we are going to record to temp spectrum file. And then the flow graph is running. I can close it now. And we can see that there is a spectrum file which has been just recorded. This is my local time. And the size, if we want to check it in megabytes, this should be pretty small. So we have already everything we need to run this from Python. Not using exactly this way of running, but using a better way, because after all, the flow graph is a Python script. So what we are going to call directly some Python class. But before I forget, there is some small difference, which is this head element. So what happens? In the way that the flow graph is now, I need to stop the flow graph manually. So I need to go play, and when I think I have enough output, I need to close this window or click this stop button. I need to do something to stop the flow graph. That's not the way in which you usually do observations automatically. Often you have a certain duration and you only record data for that duration. So the way to do that kind of duration limit in GNU Radio is to use a head block. The head block is very useful, and what it does is it only lets through the first however many items. So for example, this is set to 1024. So this will only let through 1024 items or samples, and then the flow graph will stop because it doesn't need to do any more work. So we are going to place the head block here. Basically directly at the output of the RTL-SDR, connect everything to the output of the head block, and this will limit the number of samples we read from the RTL-SDR so that we can set a certain duration for the observation, and then it will stop. And the parameter to set the duration will be called duration. I think it's, yeah. And here you can set some documentation. So observation duration in seconds. It's good to be explicit about the units. And by default, I want 10 seconds. So this will, when I use this value here, of course, I need to do something such as integer sample rate times duration, or round if you want to round the value. And with 10 seconds, this is 24 million samples, because that's 10 multiplied by the sample rate. So this will let 24 million samples go through, and then the flow graph will stop. Let's see this in action. So this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, and already it has stopped. So what's happening? I'm running the flow graph with a GUI. And when you run a flow graph with a GUI, even when the flow graph stops, the GUI doesn't close, because maybe you want to do something with these plots, or who knows. So you need to close this explicitly. But speaking of GUI, if we are going to do this automatically from a Python script, probably we don't want the GUI. You can even think that this is running on a remote machine. You only have SSH access. You cannot do X forwarding of the SSH, so you don't want any GUI. The way to do that is to set here on the options block, there is generate options, and we can set no GUI. And there are two run options. One is prompt for exit. The other one is run to completion. Run to completion is the most common I use rather than prompt for exit. So run to completion does what it says. It runs until the flow graph finishes here because the head has reached 10 seconds. And then it stops and it terminates and it returns to the terminal prompt. If you have this prompt for exit, then it says something like press enter at any time you want to stop the flow graph or something. So we set it to run to completion. And then we see that this QT GUI frequency sync is red because we cannot have GUI elements on a no GUI flow graph. So we disable this. And to test that this is working, and by the way, I'm also missing one other parameter. So here in my already made example, I want to do this 800 kilohertz frequency configurable. So this is the frequency of the translating FIR filter frequency. What have I done wrong? Yeah, typo here. Okay. So that I have a way to change this center frequency depending on the signal I want to tune to. So let's just show that this test observation, if I do help, it has the additional parameters we have set. And to demonstrate, let's do a short duration such as 3 seconds. And let's record again IQ file output to temp recording. So this runs for 3 seconds. And then it stops and I'm back at the terminal prompt. I can see that this has recorded. This is 14 minutes past the hour. So this is a freshly made recording. And I can use in Spectrum again, 200 kilohertz to see the FM signal. And it's exactly 3 seconds. Okay, so now this is working fine. And what I want to do is to control this from a Jupyter notebook, which is my favorite way of using Python, especially if I want to do plots. But before moving over to the Jupyter notebook, any questions about the flow graph?
Could you show us how the equation you use to generate the variable integrations?
Oh, yeah. The variable integrations, which is this one. So what I want to do is I want to calculate how many FFTs will give me 1 second of data. And to do that, what I know is I have sample rate samples per second. So 2.4 million samples per second. But then to make an FFT, I need an FFT, in this case, 65,000 samples. So how many FFTs per second do I have? It's sample rate divided by n FFT. And this is whatever value. And if I ask myself, well, I want a 1 second integration, then how many FFTs do I need to collect together? It's just sample rate divided by n FFT, because that's the amount of integrations that I have in 1 second. If I wanted 10 seconds, then I would need to multiply by 10. Hopefully that makes sense. And surely this number can be a floating point number. So you need to either round or take the floor or the ceiling. So that's the way to compute it. Okay.
Mm-hmm.
Okay, great. Any other questions? Okay, so let's go to the scripting folder, run Jupyter Notebook. And I already have the notebook prepared. This I'm not going to type from scratch, but I'm going to discuss what's in here. So hopefully this size is pretty large and easy to see. Let me know if you want this to be larger or smaller, but I think this is good. So what I have is I'm using pathlib for simplicity for dealing with files. We will see this later. NumPy and matplotlib. I guess all of you are familiar with NumPy and matplotlib. And the next thing we want to do is to import our Python code, which has been generated from GNU Radio. And maybe the way to motivate this is I have here my test observation.py. So it's a good recommendation to look at this with a text editor. And in fact, reading from bottom to top, what you can see is there is a main function which gets called when we run the script. The main function reads some options using the argument parser. So that's the standard Python argument parser. That's the way in which we get these nice command line arguments. And then there is this top block class, which is test observation. And it is run with a certain duration, with a certain blah, blah, blah. So these are all my parameters. So what I'm going to do in the Jupyter notebook is to call test observation with duration equal to whatever I want, etc., etc. So I'm going to call this class test observation, and then the init method of the class has duration, the frequency, the other frequency, and the output file names. But what I need to know is what is the name of the class, so that is test observation, and what's the name of the file that the class is placed in. And the name of the file just comes from the name of the GRC file. The name of the class itself is this name, and hopefully you have made both this name and the name of the GRC file the same. That's the most simple for convenience. So you have a test observation.py file that contains a test observation class. And that's the thing I want to import here. So from test observation, import test observation. This was called RTL-SDR receiver flow graph before because that's the name I used for the already made example. And then the other thing is just to set the default figure size. So let's start with a simple example about how to run the flow graph. Every time we see this flow graph name, RTL-SDR receiver flow graph, we need to change it by test observation because that is what we are running today. So the way to run this is we first create the flow graph. It is common to call it FG for flow graph, but you can call it however we want. And we can specify any parameters we want. The rest of them will have default values. So again, duration 3 seconds, just to show you. And then we need to call the run method. Why do I know we need to call the run method? You can actually see in here or in the GNU Radio documentation. So here is calling start and wait. Run is just a shorthand for start and wait. So it stands for first do start and then do wait. So if I run this, you can see that it runs. The asterisk here is still running, and in 3 seconds it finishes. So this is a simple way from Python to call your GNU Radio flow graph, and it's more simple than calling it from the terminal as we did here. because if you are using Python, if you want to run this like so, you need to use a process, the subprocess module, or you need to use system OS or something to run command line scripts, but you can do directly within Python like so, and it's so much easier. So what else do we need to make sure of? We have a VectorSync in our flow graph, and the VectorSync, if you recall, was called Spectrum VectorSync. If we go to the Python code, and in fact, I can search for Spectrum VectorSync, you can see that somewhere there is self.spectrum VectorSync equals these blocks VectorSync we have created. And if you keep searching, this is connected to some multiply constant, VXX, etc., etc. So this is our Spectrum sync. And when we go back to the Jupyter notebook, you can see that if I type flow graph Spectrum VectorSync, this is a valid object, and Python prints this is a GNU Radio VectorSync, and the address in memory where this is placed, which is not very useful 99% of the time. But you can see that you have access to this element. If you make a mistake, then it will say that test observation does not have this attribute or element. So we can access the Spectrum VectorSync in this way. We can fetch the data as indicated in the wiki page for the documentation. So we are doing .data. And I have also linked here the documentation to the source code. Often it is not necessary to read the source code in GNU Radio, but sometimes it gives you some additional details because unfortunately the documentation is not 100% complete for the blocks. So if we go to this page, which is the, where is it here? It's the VectorSync header. So this is a C++ block. It's implemented in C++ for performance. C++ is faster than Python. You can see that there is this data method which returns a vector. This will be transformed into a Python list. But there is also the reset method, which here in the documentation, I think it doesn't appear. And the reset method erases the contents of the block. And this could be useful if you are doing multiple observations, starting and stopping the flow graph. I will speak more about what I mean by starting and stopping the flow graph later on. So anyhow, just to let you know that sometimes there are some additional methods which unfortunately do not appear on the wiki page documentation, and one needs to go to the header files. So if I run this Spectrum VectorSync data, we can see that there is a bunch of numbers. This is a Python list. So what has happened here is all the data recorded by the VectorSync. We have it here now as a Python list. And that might be more convenient than recording to file, especially if you want to do some processing in GNU Radio, then do something with the data in Python. If the data is not large and it fits on your computer RAM, then you can record to one or several of these vector syncs, and it's really easy to read the data in Python. It's even easier than record to a temporary file, open the file in Python, read the data, etc., etc. In fact, it is so easy to treat the data that we can convert it to an NumPy array, which is easier to deal with. So what we do is we access the data as before, and then I'm converting to an NumPy array. So anytime I have a Python list of numbers, I can convert to an NumPy array like so. And this is a list, but what we are doing is recording vectors of NFFT. So this is 2 to the power 16 or 65,000 elements. We can also access the variable NFFT like so, flowgraph.nfft. So we are doing this reshape because if I do the reshape, my spectrum will be a matrix of 2 rows and 65,000 columns. So each column represents a different frequency, and each row represents a different time step. And I have 2 outputs, so 2 seconds worth of data. Remember that I'm doing 1 output per second, basically because I'm stopping the flow graph immediately at 3 seconds. And since we have the round to 37 in the number of integrations, maybe these integrations are slightly longer than 1 second. So no need to worry about the fact that we intended to get 3 seconds, but we only have 2 spectrum in the output. So now that we have this in an NumPy array and appropriately reshaped, it is very easy to plot the data. So for example, spectrum 0 is the spectrum at the first second. I'm also going to add spectrum 1 to show that this has recorded 2 fairly similar but also slightly different spectra in 2 second steps. So this is the first second, this is the second second. And the units I have here are linear units of power. So oftentimes we use decibel units. To convert to decibels, we use 10 logarithm 10 of the power. So this plot is in dBs. And here we go. This is a basic demonstration of how to run the flow graph within Python and how to access this data. Now, what we need to do is, I'm going to show this. If I try to run the flow graph again, so I run this cell again, what happens is I get a runtime error, and this says it's trying to open the RTL-SDR source. Runtime error failed to open the RTL-SDR source device. So what is happening? The thing that is happening here is that the previous run of the flow graph is still running because I still have a flow graph element. And until I delete this flow graph element, I do not stop the flow graph completely, and I do not free my RTL-SDR device to be used again by a second run of this flow graph or a different flow graph. So when I have finished with the flow graph and using the data in the VectorSync, I need to delete the flow graph. So to destroy this variable, we do this delete flow graph. And after doing delete flow graph, I cannot access the VectorSync anymore. Let me show this. So I cannot access anything because in fact, the name flow graph is no longer a valid variable for Python. I have deleted it completely, but I can go again and run my test observation. And what happened? Let me see. Yeah. Okay, so if you get some persistent problem like this, the thing you can do is to restart your Python script or yeah, I know what happened. Let me finish this sentence and I will explain. So if you get stuck with something is using my RTL-SDR, I don't know what it is, then kill your Python script. If it is a Python script, restart your Jupyter notebook if it's a Jupyter notebook. What was the problem I found here? So I ran the flow graph a first time doing this and it worked. Then I wanted to demonstrate that if I run this a second time, it doesn't work. But by doing so, what I have done is I have overridden the variable flow graph with a second run of the flow graph, which has failed. Yet my first run of the flow graph, which was successful, is still alive and unbound to any Python variable. So I have no real way to kill it rather than restarting the flow graph. maybe the proper way to demonstrate this would have been that I can run this, I can run all of this again, and that if I want to run this here below, I need to delete this flow graph, which I have already done, and I can run the flow graph again, and I can delete the flow graph again. So the test pattern is very clear. You run the flow graph, you do something with the flow graph, for example, read data out of the Spectrum VectorSync, and finally you delete the flow graph, and then you can run the flow graph again. So now we come to the fun part, which is an example observation in quotes, because this is not a real observation with a telescope. It's just my RTL SDR stick. But we are going to look at a few interesting frequencies on the radio frequency spectrum. I have selected this beforehand. I was doing this preparation the other day, seeing in my local spectrum which signals are strong and interesting, and in what frequencies it could make sense to record. But if you are doing a radio frequency interference scan, maybe you can have a list of frequencies which looks like frequencies equals anything from 100 to 800 megahertz in steps of 2 megahertz, which is good because the RTL SDR covers 2.4 megahertz. So by doing this, you get a huge list of frequencies to record that. So 100 megahertz, 102, 104, etc., etc. There are many frequencies. And if you spend 10 seconds per frequency, then this is dot size. You're going to spend the best part of an hour recording, but that's quite good for many kinds of RFI scans. So this is a good way to do RFI scanning. For today, we have this pre-selected list of frequencies and also the frequencies for the frequency translating FIR filter. So what this means is that there is something at 98.8 megahertz that we want to record. Also something at 95.8. So 95.5 plus 300 kilohertz is 95.3. Also 117.3 if you subtract these two, etc., etc. Duration 10 seconds for everything. We could have this as complicated as we wanted. And what I'm going to do is to save the spectrum data for each of these observations. So each of these represents a different scan. They are more commonly called scans in radio astronomy. So let's call these scans. So for each of the scans, I'm going to put the output in a dictionary. And I'm going to save all the output in a path, which is /temp/observation. This will be a directory. So I'm going to use, this is the reason I'm using pathlib. If you're handy with Python, you can use pathlib to do all sorts of stuff with files, paths, and directories. So for example, here I'm creating this temp observation directory with the make dir, and it's okay if it already exists because it's the second time I run this. And what I'm going to do is to iterate through the list of frequencies to scan and the frequency translating frex with this zip. So the zip will give me pairs of radio frequency and the translating frequency to use for the flow graph. And this is pretty much how real world radio astronomy observations look like. They are oftentimes Python script with some kind of for loop because we want to observe different sources to do different scans, and we do several steps for each of them. So the steps we are going to do here are we print a message just to keep note of progress receiving on this frequency and tuning to this frequency. Then the path for my IQ file, I'm going to use my output directory. If you're using pathlib, you can combine paths with slash. So I'm going to call this IQ data, and I'm going to use the R frequency so that I get a different file for each of the different frequencies. And the file will contain the frequency in its name. And also, if we are storing this for long, it's a good idea to put the samples per second in the file name, and also the format. This is complex 64, so it's the format we're recording. An alternative to having these awkward names with frequency, sample rate, and format is to use SIGMF. Probably I will speak about SIGMF in another session. That gives you a way of having metadata attached to your recordings, and the metadata holds the information for the frequency, the sample rate, and also whatever else you want. If this was a real observation, maybe you want to record the right ascension and declination that the telescope is pointing to, or who knows. So once we have calculated all the parameters we want to use, what we do is we call our test observation with duration equals duration, frequency equals this RF frequency variable that we get from here. Frequency translating frequency is the frequency that we get from this list. And the IQ file output equals IQ file. I'm not using the file output for the spectrum because I'm going to use the VectorSync for the spectrum. So I have my flow graph, I run it, and then what I do is to save the spectrum data. So spectrum data is a dictionary. I'm indexing it by the frequency. It's maybe not the best idea, but it works. And this is exactly as above. I'm using .data to get the data from the VectorSync, convert into an NumPy array, and reshaping. And then I delete my flow graph so that in the next iteration of the for loop, we can create again a test observation flow graph and run it. So let's go and run it. It says receiving on 98 megahertz, tuned to 800 kilohertz, and it will do so for 10 seconds. Let's go and check. There is IQ data 98 megahertz, and there is also IQ data 95.5 megahertz because 10 seconds have already passed. So now I have receiving on 95.5 megahertz, receiving on 117.5 megahertz, and it's basically going through my list of frequencies, putting this spectrum data in the dictionary, which we will use later on, and storing the IQ data for only 200 kilohertz of spectrum in these files. So while this finishes to run, any questions so far? Okay, I think it's only 10 or 20 seconds more to go. So what we can do while this finishes is to invest some time in looking at the recorded data. So in spectrum again, 200 kilohertz. This is yet again the same FM radio station, so nothing new. You can see that the recorded data is exactly 10 seconds. The one with 95.5 megahertz is yet another FM radio station, and you can see that the signal looks different because the kind of music that is played is probably different. And with some experience, it's even possible to see if this is voice or if it's music, what kind of music it might be, because basically the sound waveform affects how the frequency modulation spectrum looks like. Okay, so now this has finished. And what do we want to do? I have some nice plots prepared, but before going with those, we have spectrum data. So let's check what is spectrum data. So spectrum data is a dictionary. The indices are frequencies such as 98 megahertz, 95.5, etc. And the contents are NumPy arrays, which hopefully will have 10 or 9 rows because we have recorded for 10 seconds, and 65,000 columns because we are using 65,000 points FFT bins. And this is some boilerplate Python code to plot results. Probably you know how to plot with Python, so let me go very quickly through that. What I'm going to do is, because we have 65,000 points in the spectrum, it's not very convenient to plot those as an image. So basically, I want to produce this kind of plot. I have the spectrum versus time. So this is also called waterfall, from 0 to 10 seconds. Plotted as an image using imshow. And I also have the average spectrum for all of this. So what I was saying is that if we attempt to plot 65,000 columns in this image, then there is not enough resolution on the screen. Python will need to do some kind of downscaling. And in that downscaling, we can lose fine narrow theaters of the plot, such as these RFI lines. So it's a better idea to reduce the number of frequency bins we plot for the image. For this line plot, it's okay. We are plotting the 65,000 FFT bins, but for this one, we are not. And what we have is this waterfall frequency reduce. And we basically group our 65,000 FFT bins in groups of 64, so that we have only 1,024 groups, and then compute the maximum within each of those groups. You could compute the minimum or the average. It depends on what you want to do. And to do that, what am I doing? I have a frequency axis correctly set for the plot. So here, this is at 98 megahertz and goes to 99 point something. So this whole range is 2.4 megahertz. How can I do that? I can use this FFT frec with the number of FFT bins and the sample rate, 1 divided by the sample rate, like so. I also need an FFT shift. I want to have 2 plots, so plots. Then this slightly complicated expression with the reshape does what I explained before. It's doing groups of 64 adjacent frequency bins, and it's taking the maximum of each group. So that's the reason I have maximum, but only on axis -1. And what else? ImShow, this is to plot the image. So we convert to dBs, and we properly set the extent for the frequency range, because otherwise the 2 plots are not going to line up correctly. And what else? Yeah, the second plot, which is the line plot of the frequency average, is fairly simple. So average across the time axis, convert to dBs, and here I have the appropriate frequency axis, adding the center frequency, which I'm getting because it's here in the Python dictionary key. So let's look at the results we have obtained to see what kind of different signals there are out there. This is the FM radio stations we have been using all the morning. These are other FM radio stations. So this was 98 megahertz. This is 95.5. From 80 something to 110 or so, or maybe only 105. It's the FM broadcast band. So if you go across it, you'll find different FM stations. What else? Around 110 to 130, we have aircraft signals. So we have both aircraft radio navigation signals that the planes use to find the routes and find airports, do approaches to airports and so on. And also we have voice communications of airplanes, the control tower, etc. And these in particular, you can see this line here and here. The rest is RFI. But this is an airplane radio navigation beacon, which is close by, maybe 6 kilometers from where I live. So this is something else you can receive with your RTL-SDR if you are near an airport. What else? Here at 400 and something megahertz is probably a police radio station, or the fire department, or ambulances, or something like that. It's called Tetra. We use it in Europe for digital voice. In the US, you have something similar, which is called P25. And I think it's also around 400 megahertz. So you have voice communications for those kind of services. And most frequently, they are encrypted, so you cannot listen on the police by tuning to this frequency. But even so, this provides a really strong signal. So you can see this is 1070. So it's about 60 dB signal to noise ratio. And we will use it later on to demonstrate aliasing effects and how to do downsampling properly. What else? Higher up at 800 megahertz, we have some cell phone communication signals. So this is LTE. It's the 4G, fourth generation cell phone communication standard. I think there are similar bands on the United States at 700, 800 megahertz. So yet other good bands to tune to with your RTL-SDR. This you can see here is actually 10 megahertz wide. So it starts here, but it extends much farther than the plot. And since the RTL-SDR has only 2.4 megahertz of bandwidth, you cannot receive this complete LTE signal. But there is this auxiliary signal, which is called narrowband IoT for Internet of Things, and it's 200 kilohertz also. So this fits completely in the RTL-SDR. What else? 935 megahertz. This is a GSM frequency. GSM is the first generation of cell phone technology. It's being phased out in the United States, so maybe you don't even find these signals anymore, but it's still common in other parts of the world. And finally, another good one, 1090 megahertz. This is RFI, so this is not the signal I want to show. The signal I want to show is basically here. It's also all the time, but here it is stronger. The rest of the time is so weak that it's difficult to see. Maybe you can also see here in the average, though there is a bunch of RFI, so it's not easy to see. So what is this signal? This is called ADSB. And ADSB is a transmitter which is carried by airplanes, and they transmit their position pretty much continuously. And if you have seen online any of those maps where they show in real time where all the airplanes in the world are, they use data received by ADSB, and you can also do that with your RTL-SDR stick. So you can download a free open source ADSB receiver and use it to receive this data and plot the airplane positions on your computer. But in here, it's just another frequency we can tune to, and I wanted to show this in Spectrum because it's a very peculiar signal. So hopefully we have it here. And oh, that's so bad. Have I run this again? Okay, no. Yeah, that was a good one. So what I was showing and commenting on was basically the version of the plot that you have on here, sorry, which is when I did this notebook on the weekend. So this is the thing I was commenting. Here you see the signal, and most of the signals look the same. This is the data for the recording we have done just now. But in here, there is no signal. So what has happened is, unfortunately, there were no airplanes flying nearby when I was recording this some minutes ago. So we don't have any ADSB signal. I wanted to show how this looks like in Spectrum. I will just explain, and maybe I will prepare a good recording for another day. The ADSB signal are pulses, so very short pulses. And it's interesting because it can be received with a small SDR pretty much anywhere in the world, because pretty much anywhere you have airplane traffic. And it gives you a good example of pulsed signal if you are interested in detecting pulses, canceling pulsed RFI or similar things. What else? That's everything regarding this demonstration about how to run a GNU Radio flow graph from Python code, either a Jupyter notebook or standalone Python script. You can see that it would be really simple to turn this into a standalone Python script that even saves the PNG plots for you in a folder or something. A comment is probably worth to do now, which is this is the simple way of conducting an observation in which you have multiple targets, multiple outputs to be produced. But what happens is that for each of the scans, we are initializing the SDR again. So basically, we are starting from scratch. We are stopping GNU Radio completely. We are starting the RTL SDR again. And it takes a couple seconds to start the RTL SDR. So you might prefer not to do it for each of your scans. But the most important reason to start the SDR just one time and then do all the observations without restarting is because there are some calibrations which are only good when you do not restart the SDR. So if you need to do any of those calibrations, then this way of observing is no good, because you would do one of the calibration scans, but then you are restarting the SDR and you are losing your calibration. So there is a more advanced way to conduct an observation like this without restarting the flow graph for each of the scans. And that has to do with something that is called stopping and resuming the flow graphs. Yeah, there I had it. So you can read more about this in this handling flow graphs page. There is this about reconfiguring flow graphs, and you can reconfigure pretty much everything. You can delete blocks, add new blocks, reconnect blocks. And basically, the way to do this is you need to do this lock to temporarily stop the flow graph. You can change some of the settings. So for example, if you are recording to VectorSync, you would use that reset, or was the reset, this reset to delete all the previous output. And then you can resume the flow graph again using unlock. If you have a file sync and you want to change the file, you basically need to throw away the file sync and create a new file sync. So you need to create a new file sync, disconnect the previous one, connect the new one, and delete the previous one. So it's a bit cumbersome, but the main advantage is that it's very flexible. You can basically restructure your flow graph as deeply as you want, and you can stop and resume as you want. So this is the more advanced way of doing the same thing. And in some situations, it's actually the only possible way if you have this requirement not to restart the SDR within different scans. Okay, so questions about this? Okay, I suggest we stop 5 minutes. That's basically until the top of the hour. And I'm going to prepare the next thing for today, which is some demonstration about how the frequency translation FIR filter works in more detail. Okay, let's continue. So let me come back to this. Yeah. What I have now is essentially the same flow graph as before. I have tuned to 425 megahertz. That's the very strong police radio station or something that we had. And I only have the frequency sync. So I have a strong signal here and nothing else going on, which is good to demonstrate how to correctly move this frequency, this signal in frequency, how to decimate, what is aliasing, how we might make mistakes with the frequency translating FIR filter. So for now, let's just see that the signal is at about 250 kilohertz, minus 250 kilohertz. So if we want to move that to the center, we can use the frequency translating FIR filter, but I'm going to set a decimation of 1. So here I have 1. For the taps, I'm going to do 1, which means no filtering. If you remember something about FIR filters, if you have learned about those do a mathematical operation called the convolution with a sequence of taps. And if you have just a single one as your taps, then that's equivalent to doing no filtering. It means the output of the filter is equal to the input of the filter. So taps of 1, or to be more correct, a list of just a single one. And then the center frequency, I'm going to set minus 250 kilohertz. And for comparison, I'm going to set this to 2 inputs. So the first input will be blue, the second input will be red. And what this flow graph does, no surprises, the signal was originally here at minus 250, and now it has moved 250 kilohertz to the right, so that it's now in the center. Because when doing signal processing, it is very common to process signals which are centered at 0 at baseband. So moving our signal of interest to baseband is usually one of the first steps we want to do. Okay, what happens next? If we want to decimate, so we want to decimate by 12, that means for each 12 input samples, we have a single output sample. So the output sample rate has been reduced by a factor of 12, and it's now 200 kilohertz. I could try to do this like this, and of course it's wrong. There's a reason why a low-pass filter needs to be set in the taps, but I'm going to demonstrate why this is wrong, how it happens, how you can realize it has happened. So basically, I'm doing decimation, but no low-pass filter taps. Then here I have more or less the same, but the bandwidth is 200 kilohertz. And this looks more or less all right. I mean, it's the same signal. It looks wider because this is displaying just a 200 kilohertz slice. But if I do the same here, more or less, it's more or less the same. However, if you were to measure the signal to noise ratio here, from minus 35 to minus 80, and here from minus 23 to minus 74, you would probably realize that here we have lost some signal to noise ratio. And I will come back to that in a moment. But the thing that I want to show is what would happen if there were other signals. And here I don't have other signals. So what I'm going to do is to pretend that instead of tuning to this signal, we want to tune to this empty area here around minus 370. And I have chosen minus 370 because minus 370 plus 100 is 270, which is about here, sorry. So basically it's near the limit of our signal. Basically, I want to select this area, which is just to the right of our signal. And we would expect only to get this noise, which is below the box I'm drawing. We would expect the strong signal to disappear in the output. So let's do the exercise. If instead of doing it like this, I put here minus 370, then the red plot is without decimation, so this works correctly. Our signal is just above 100 kilohertz, and between minus 100 kilohertz and plus 100 kilohertz, there is only noise. So we would expect the same thing to hold true in the above plot, where we have decimated by 12. However, what happens is we have our signal here at minus 78 or something. And of course, if we look at the red spectrum at minus 78, there is nothing. So this is called aliasing. And the way to understand aliasing is the following. We have here, let me just have the red one. We have here 2.4 megahertz of spectrum, and we want to convert that into 200 kilohertz of spectrum. So it is true that the central 200 kilohertz, so from minus 100, from minus 100 to plus 100, will end up as here in the output. But also, if I continue, what happens is basically I'm wrapping around all the spectrum several times on the output. So if I continue above 100, what I encounter here, so for example, this signal appears here. And in fact, we can see the signal is slightly above 100, so it has appeared here. And this effect is called aliasing. So we say an alias of the signal is here in the decimated output. And then we can continue from 100 to 300. And all the signals we have in here appeared on top of the output spectrum. And if we continue once again from 300 to 500 again, and that not only happens for signals, but also for the noise. So all the noise we have in here, we are adding multiple times worth of noise. And that's the reason why the signal to noise ratio of this signal is smaller, because the noise we see here is not only the noise around the signal, but also at multiples of 200 kilohertz away of the signal. So there are actually 12 copies of the noise, and the signal to noise ratio would have decreased by 13 dBs, if I'm correct, because no, 10, basically 10 dBs, which is 12 in dB units. So yeah, that's unfortunate, because on the output we only want from minus 100 to plus 100. We do not want to repeat everything in the spectrum, wrapping it around 12 times. We just want the central wraparound. The way to achieve that is, before doing this decimation, to use a low-pass filter that eliminates everything which is outside of minus 100 to plus 100. And the kind of filter that does that is a low-pass filter with a cutoff frequency of 100. And such a low-pass filter will let everything between minus 100 and plus 100 through, and everything which is at a higher frequency will be heavily attenuated. So it will still be present in the output, but many dBs down, and it can be ignored because it's below the noise. So, okay, so far so good. How do we do this low pass filter? There is this low pass filter tabs, which is a simple way of defining a low pass filter, or we can also use directly filters, low pass, etc., as I did before. This is just a way of calling this block in Python. So the parameters for this block will be the same parameters that would you use here in filters.lowpass. So which to use depends on your preference, basically. Let's call these tabs, and the parameters are gain. The gain just defines if everything is amplified or attenuated. It basically doesn't matter unless you want your output signal to be a particular amplitude, in which case you might be interested in setting a different gain from 1. The input sample rate is important to set because everything else will be related to the sample rate. And then the cutoff frequency, we said we want to cut at 10 kilohertz, and the transition width is usually a fraction of the cutoff frequency, for example, 10% or something similar, because what happens is that we cannot have a filter which lets everything up to 100 kilohertz through and makes completely disappear everything above 100 kilohertz. That's mathematically impossible. Every filter which is mathematically realizable needs to have a smooth transition between letting signal through and attenuating signal. And how fast that transition happens, which is also called as the filter skirt, is defined by the transition width. A narrower width will make the skirt steeper and will require more coefficients for the tabs. So it will need more CPU power to run the filter. So I can set the tabs here for the moment, just in this one. And what happens is now you can see the effect on the red thing. So we have up to 100 kilohertz. I'm going to turn up the average to make this easier to see. Up to 100 kilohertz, the filter is letting everything through without attenuation. And beyond 100 kilohertz, we have the filter skirt. In fact, it's more useful to look at this one first, where there is no signal. So within 10 kilohertz, because that's the transition width we have specified. So basically from minus 95 to plus 105, the filter goes from no attenuation to an attenuation of, I don't know, probably more than 60 dBs, maybe 80 dBs. It depends on how you design the filter. So depending on the situation, you might need more attenuation, or you might do with a filter which doesn't have so much attenuation. And then the filter attenuates the rest of the signal, and this is already pretty low, so all of these can be ignored. We also see the signal here. So what happens is the signal was about 60 dBs above the noise. So even though the filter is attenuating it, it is here and it will slightly be present on the output. If we really needed to suppress the signal completely, we would need a more steep filter or to set up the filter differently to avoid the signal. But still, you can see that when I have this red thing and I wrap it again and again and again on the output, essentially I'm only going to get this piece because the rest is very much attenuated. So I'm going to replace the tabs also here. And now you can see that we don't have the signal, which is what we wanted. Basically, the signal is still doing a small contribution here I'm not sure if with some averaging, probably not, it will be possible to detect. So the thing we have obtained here is basically what we wanted is just only this 100 kilohertz portion. So that's the thing you need to remember. When you want to decimate, you need to run this low pass filter first, which is called an anti-alias filter, to remove everything which would end up outside of your passband, because if you don't remove it, it will alias back and it will interfere with whatever you try to receive here. So now that we understand this better, what is the usual way to set this up without thinking too much? So if you actually, I'm going to use a variable. I have a variable, which is decimation. Let me replace it here, decimation. So if you want to think about the cutoff frequency, the cutoff frequency was 100 kilohertz because our output goes from minus 100 kilohertz to plus 100 kilohertz because our output sample rate is 200 kilohertz. Remember that in 200 kilohertz, you can represent signal from minus 100 to plus 100. And in general, you can represent signals from minus half of the sampling frequency to plus half of the sampling frequency. So we usually want to set the cutoff frequency at half of the output sampling frequency, which is 1/2 multiplied by the sample rate divided by the decimation. And this is 100 kilohertz. So without thinking too much, and this will also serve for every decimation you decide to put in, you can use this cutoff frequency. How about the transition width? As I mentioned, this is usually set to some percentage of the cutoff frequency. So for example, doing 0.1, or which is 10%, or 0.05, which is 5%, are common values. And depending on how tight you set this, so depending on how small you set this, you will have more or less filter coefficients. So if you look at these tabs, there are 289 tabs with 10% transition bandwidth. With 5%, there are now 579. So it depends on how fast your CPU is, on whether you want to do this in real time, what's your sample rate, because of course it's not the same to filter samples at 2 megahertz as we're doing here. That's relatively small, as filtering things at several hundred megahertz. That's much more CPU intensive. So it depends on the setting, but usually 10% is a fine choice for most of the stuff we will do. And when we set these values, that is basically the same thing we had, except the transition bandwidth is now 20 kilohertz. So now we can see that since the filter transition is wider, there is still a small piece of the signal which is appearing here. Let me average. So this small part of the signal is this small part of the signal, which is actually this part of the signal. But that is fine, because when you set the 10% transition bandwidth, what you say is that 5% of your spectrum here, it's potentially going to contain aliases, so you will not use it, and also 5% of the bandwidth here. So that makes up for the total 10% transition we had. And that's what happens basically. Since ideal filters which go immediately from no attenuation to infinite attenuation do not exist, every time we are dealing with digital signals, the edges of the passband at best need to be handled with caution, and at worst they should be ignored because they can contain aliasing from outside, as this demonstrates. What else I can show? The way to check if all this is going correctly. usually if you set not 0.5 for the cutoff frequency, so exactly this frequency, you will get something more or less flat here because there is some attenuation starting on the filter right before, but there is also some noise from outside aliasing here. So the two effects basically add up and you end up with something which is flat. If you prefer to have something which is not flat and to have something which makes it more evident that the outsides of the passband should not be used, you can set 45% instead of 50% or even 40%. And the cutoff of the filter will happen sooner. Here you can see the start of the filter. And since we are starting sooner, now the signal is completely attenuated. So that might be something that you prefer to do. It depends on what you are trying to do exactly. If your signal is in the middle using only this area, then it doesn't matter so much what you do on these edges. But if your signal uses a wide part of all these 200 kilohertz window, then you might want to be more careful of what you do at the edges. And of course, if you make a mistake and you use 0.6 here, which is too large, then what happens is you can see here the noise floor slightly increases because now the filter skirt starts farther away, but we have noise coming in from aliasing. So if you get this rising noise floor, then that's already an indication you are doing something incorrectly. And then we have this signal, which is because we are starting the filter afterwards. So here, then all the signal aliases completely. And by the way, we also have this signal, which has disappeared now. That was another radio station, which was not active before and has appeared for a few minutes and disappeared. Who knows? Another brief transmission of someone. So that might happen when you are watching a live radio frequency spectrum. Signals might appear and disappear. This could be someone talking on their digital radio or whatever. So, okay, this is pretty much what I had for today. Any questions about aliasing or anything of what we saw?